The Sun is the star at the center of the Solar System. It is a nearly perfect sphere of hot plasma, with internal convective motion that generates a magnetic field via a dynamo process. It is by far the most important source of energy for life on Earth. Its diameter is about 109 times that of Earth, and its mass is about 330,000 times that of Earth, accounting for about 99.86% of the total mass of the Solar System. About 3/4 of the Sun's mass consists of hydrogen. The rest is mostly helium, with much smaller quantities of heavier elements, including oxygen, carbon, neon, and iron. The Sun is a G-type main sequence star based on spectral class and is informally referred to as a yellow dwarf. It formed approximately 4.6 billion years ago from the gravitational collapse of matter within a region of a large molecular cloud. Most of this matter gathered in the center, whereas the rest flattened into an orbiting disk that became the Solar System. The central mass became so hot and dense that it eventually initiated nuclear fusion in its core. It is thought that almost all stars form by this process. The Sun is roughly middle-aged and has not changed dramatically for over 4 billion years, and will remain fairly stable for more than another 5 billion years. However, after hydrogen fusion in its core has stopped, the Sun will undergo severe changes and become a red giant. It is calculated that the Sun will become sufficiently large to engulf the current orbits of Mercury, Venus, and possibly Earth. The enormous effect of the Sun on Earth has been recognized since prehistoric times, and the Sun has been regarded by some cultures as a deity. The synodic rotation of Earth and its orbit around the Sun is the basis of the solar calendar, which is the predominant calendar in use today. Name and etymology. The English proper noun sun developed from Old English sun and may be related to south. Cognates to English sun appear in other Germanic languages, including Old Frisian sun, son, Old Saxon sonne, Middle Dutch son, Modern Dutch zon, Old High German sonne, Modern German son, Old Norse sonne, and Gothic sonno. All Germanic terms for the sun stem from Proto-Germanic *sun, and the English weekday name Sunday stems from Old English and is ultimately a result of a Germanic interpretation of Latin dies solus, itself a translation of the Greek mu epsilon rho alpha lambda iota omicron upsilon. The Latin name for the Sun, Sol, is not common in general English language use. The adjectival form is the related word solar. The term Sol is also used by planetary astronomers to refer to the duration of a solar day on another planet, such as Mars. A mean Earth solar day is approximately 24 hours, whereas a mean Martian Sol is 24 hours, 39 minutes, and 35.244 seconds. Religious aspects. Solar deities and sun worship can be found throughout most of recorded history in various forms, including the Egyptian Ra, the Hindu Surya, the Japanese Amaterasu, the Germanic Sol, and the Aztec Tonatiuh, among others. From at least the 4th dynasty of ancient Egypt, the sun was worshipped as the god Ra, portrayed as a falcon-headed divinity surmounted by the solar disk, and surrounded by a serpent. In the New Empire period, the sun became identified with the dung beetle, whose spherical ball of dung was identified with the sun. In the form of the sun disk Aten, the sun had a brief resurgence during the Amarna period when it again became the preeminent, if not only, divinity for the pharaoh Akhenaten. The sun is viewed as a goddess in Germanic paganism. Sol, sun. Scholars theorize that the sun, as a Germanic goddess, may represent an extension of an earlier Proto-Indo-European sun deity because of Indo-European linguistic connections between Old Norse Sol, Sanskrit Surya, Gaulish Sulis, Lithuanian Sol, and Slavic Solansa. In ancient Roman culture, Sunday was the day of the sun god. It was adopted as the Sabbath day by Christians who did not have a Jewish background. The symbol of light was a pagan device adopted by Christians, and perhaps the most important one that did not come from Jewish traditions. In paganism, the sun was a source of life, giving warmth and illumination to mankind. It was the center of a popular cult among Romans, who would stand at dawn to catch the first rays of sunshine as they prayed. The celebration of the winter solstice was part of the Roman cult of the unconquered sun. Christian churches were built with an orientation so that the congregation faced toward the sunrise in the east. Characteristics. The Sun is a G-type main sequence star that comprises about 99.86% of the mass of the Solar System. The Sun has an absolute magnitude of plus 4.83, estimated to be brighter than about 85% of the stars in the Milky Way, most of which are red dwarfs. The Sun is a population I, or heavy element-rich, star. The formation of the Sun may have been triggered by shock waves from one or more nearby supernovae. This is suggested by a high abundance of heavy elements in the Solar System, such as gold and uranium, relative to the abundances of these elements in so-called population II, heavy element-poor, stars. The heavy elements could most plausibly have been produced by endothermic nuclear reactions during a supernova, or by transmutation through neutron absorption within a massive second-generation star. The Sun is by far the brightest object in the sky, with an apparent magnitude of minus 26.74. This is about 13 billion times brighter than the next brightest star, Sirius, which has an apparent magnitude of minus 1.46. The mean distance of the Sun's center to Earth's center is approximately 1 astronomical unit, though the distance varies as Earth moves from perihelion in January to aphelion in July. At this average distance, light travels from the Sun's horizon to Earth's horizon in about 8 minutes and 19 seconds, while light from the closest points of the Sun and Earth takes about 2 seconds less. The energy of the sunlight supports almost all life on Earth by photosynthesis, and drives Earth's climate and weather. The Sun does not have a definite boundary, and in its outer parts its density decreases exponentially with increasing distance from its center. For the purpose of measurement, however, the Sun's radius is considered to be the distance from its center to the edge of the photosphere, the apparent visible surface of the Sun. By this measure, the Sun is a near-perfect sphere with an oblateness estimated at about 9 millionths, which means that its polar diameter differs from its equatorial diameter by only 10 kilometers. The tidal effect of the planets is weak and does not significantly affect the shape of the Sun. The Sun rotates faster at its equator than at its poles. This differential rotation is caused by convective motion due to heat transport and the Coriolis force due to the Sun's rotation. In a frame of reference defined by the stars, the rotational period is approximately 25.6 days at the equator and 33.5 days at the poles. Viewed from Earth as it orbits the Sun, the apparent rotational period of the Sun at its equator is about 28 days. Sunlight. The solar constant is the amount of power that the Sun deposits per unit area that is directly exposed to sunlight. The solar constant is equal to approximately 7 quintillion 3 quadrillion 136 trillion 800 billion spade suit 1368 W per square meter at a distance of 1 astronomical unit from the Sun. Sunlight on the surface of Earth is attenuated by Earth's atmosphere, so that less power arrives at the surface in clear conditions when the Sun is near the zenith. Sunlight at the top of Earth's atmosphere is composed of about 50% infrared light, 40% visible light, and 10% ultraviolet light. The atmosphere in particular filters out over 70% of solar ultraviolet, especially at the shorter wavelengths. Solar ultraviolet radiation ionizes Earth's day-side upper atmosphere, creating the electrically conducting ionosphere. The Sun's color is white, with a CIE color space index near when viewed from space or when the Sun is high in the sky. When measuring all the photons emitted, the Sun is actually emitting more photons in the green portion of the spectrum than any other. When the Sun is low in the sky, atmospheric scattering renders the Sun yellow, red, orange, or magenta. Despite its typical whiteness, most people mentally picture the Sun as yellow. The reasons for this are the subject of debate. The Sun is a G2V star, with G2 indicating its surface temperature of approximately 5,778 K, and V that it, like most stars, is a main sequence star. The average luminance of the Sun is about 1.88 gigacandela per square meter, but as viewed through Earth's atmosphere, this is lowered to about 1.44 GCD per square meter. However, the luminance is not constant across the disk of the Sun. Composition. The Sun is composed primarily of the chemical elements hydrogen and helium. They account for 74.9% and 23.8% of the mass of the Sun in the photosphere, respectively. All heavier elements, called metals in astronomy, account for less than 2% of the mass, with oxygen, carbon, neon, and iron being the most abundant. The Sun inherited its chemical composition from the interstellar medium out of which it formed. The hydrogen and helium in the Sun were produced by Big Bang nucleosynthesis, and the heavier elements were produced by stellar nucleosynthesis in generations of stars that completed the stellar evolution and returned their material to the interstellar medium before the formation of the Sun. The chemical composition of the photosphere is normally considered representative of the composition of the primordial solar system. However, since the Sun formed, some of the helium and heavy elements have gravitationally settled from the photosphere. Therefore, in today's photosphere the helium fraction is reduced, and the metallicity is only 84% of what it was in the protostellar phase. The protostellar Sun's composition is believed to have been 71.1% hydrogen, 27.4% helium, and 1.5% heavier elements. Today, nuclear fusion in the Sun's core has modified the composition by converting hydrogen into helium. So the innermost portion of the Sun is now roughly 60% helium, with the abundance of heavier elements unchanged, because heat is transferred from the Sun's core by radiation rather than by convection. None of the fusion products from the core have risen to the photosphere. The reactive core zone of hydrogen burning, where hydrogen is converted into helium, is starting to surround an inner core of helium ash. This development will continue and will eventually cause the Sun to leave the main sequence, to become a red giant. The solar heavy element abundance is described above are typically measured both using spectroscopy of the Sun's photosphere and by measuring abundances in meteorites that have never been heated to melting temperature. These meteorites are thought to retain the composition of the protostellar Sun and thus not affected by settling of heavy elements. The two methods generally agree well. Singly ionized ion group elements. In the 1970s, much research focused on the abundances of ion group elements in the Sun. Although significant research was done, until 1978 it was difficult to determine the abundances of some ion group elements via spectrography because of the hyperfine structures. The first largely complete set of oscillator strengths of singly ionized ion group elements were made available in the 1960s, and these were subsequently improved. In 1978, the abundances of singly ionized elements of the ion group were derived. Isotopic composition. Various authors have considered the existence of a gradient in the isotopic compositions of solar and planetary noble gases, e.g., correlations between isotopic compositions of neon and xenon in the Sun and on the planets. Prior to 1983, it was thought that the whole Sun has the same composition as the solar atmosphere. In 1983, it was claimed that it was fractionation in the Sun itself that caused the isotopic composition relationship between the planetary and solar wind implanted noble gases. Structure. The core of the Sun extends from the center to about 20 to 25% of the solar radius. It has a density of up to 7 quintillion 5 quadrillion 150 trillion spadesuit 150 grams per cc and a temperature of close to 15.7 million kelvins. By contrast, the Sun's surface temperature is approximately 5,800 K. Recent analysis of SOHO mission data favors a faster rotation rate in the core than in the radiative zone above. Through most of the Sun's life, energy is produced by nuclear fusion in the core region through a series of steps called the PP chain. This process converts hydrogen into helium. Only 0.8% of the energy generated in the Sun comes from the CNO cycle, though this proportion is expected to increase as the Sun becomes older. The core is the only region in the Sun that produces an appreciable amount of thermal energy through fusion. 99% of the power is generated within 24% of the Sun's radius, and by 30% of the radius, fusion has stopped nearly entirely. The remainder of the Sun is heated by this energy as it is transferred outwards through many successive layers, finally to the solar photosphere where it escapes into space as sunlight of the kinetic energy of particles. The proton-proton chain occurs around 7 quintillion 37 quadrillion 919 trillion 999 billion 999 million 999,999 spadesuit 9.2 times 1037 times each second in the core, converting about 3.7 times 1038 protons into alpha particles every second, or about 6.2 times 1011 kilograms per second. Fusing 4 free protons into a single alpha particle releases around 0.7% of the fused mass's energy, so the Sun releases energy at the mass-energy conversion rate of 4.26 million metric tons per second for 384.6 yatawatts, or 9.192 times 1010 megatons of TNT per second. Theoretical models of the Sun's interior indicate a power density of approximately 276.5 W per cubic meter, a value that more nearly approximates reptile metabolism than a thermonuclear bomb. The fusion rate in the core is in a self-correcting equilibrium. A slightly higher rate of fusion would cause the core to heat up more and expand slightly against the weight of the outer layers, reducing the density and hence the fusion rate and correcting the perturbation, and a slightly lower rate would cause the core to cool and shrink slightly, increasing the density and increasing the fusion rate and again reverting it to its present rate. Radiative zone from the core out to about 0.7 solar radii. Thermal radiation is the primary means of energy transfer. The transfer of energy through this zone is by radiation, not by thermal convection. The temperature drops from approximately 7 million to 2 million kelvins with increasing distance from the core. This temperature gradient is less than the value of the adiabatic lapse rate and hence cannot drive convection. Hence, energy is transferred by radiation. Ions of hydrogen and helium emit photons, which travel only a brief distance before being reabsorbed by other ions. The density drops 100-fold from 0.25 solar radii to the 0.7 radii at the top of the radiative zone. Tachocline. The radiative zone and the convective zone are separated by a transition layer, the tachocline. This is a region where the sharp regime change between the uniform rotation of the radiative zone and a differential rotation of the convection zone results in a large shear between the two, a condition where successive horizontal layers slide past one another. The fluid motion of the convection zone above slowly disappears from the top of this layer to its bottom, where it matches that of the radiative zone. Presently, it is hypothesized that a magnetic dynamo within this layer generates the Sun's magnetic field. Convective zone. The Sun's convection zone extends from 0.7 solar radii to near the surface. In this layer, the temperature is lower than in the radiative zone and heavier atoms are not fully ionized. As a result, radiative heat transport is less effective and convection moves the Sun's energy outward through this layer. The density of the plasma is low enough to allow convective currents to develop. Material heated at the tachocline picks up heat and expands, thereby reducing its density and allowing it to rise. As a result, an orderly motion of the mass develops into thermal cells that carry the majority of the heat outward to the Sun's photosphere above. Once the material diffusively and radiatively cools just beneath the photospheric surface, its density increases, and it sinks to the base of the convection zone, where it again picks up heat from the top of the radiative zone and the convective cycle continues. At the photosphere, the temperature has dropped to 5,700 K and the density to only 0.2 grams per cubic meter. The thermal columns of the convection zone form an imprint on the surface of the Sun, giving it a granular appearance called the solar granulation at the smallest scale and supergranulation at larger scales. Turbulent convection in this outer part of the solar interior sustains small-scale dynamo action over the near-surface volume of the Sun. The Sun's thermal columns are Bénard cells and take the shape of hexagonal prisms. Photosphere. The visible surface of the Sun. The photosphere is the layer below which the Sun becomes opaque to visible light. Above the photosphere, visible sunlight is free to propagate into space, and its energy escapes the Sun entirely. The change in opacity is due to the decreasing amount of H- ions, which absorb visible light easily. Conversely, the visible light we see is produced as electrons react with hydrogen atoms to produce H- ions. The photosphere is tens to hundreds of kilometers thick, and is slightly less opaque than air on Earth, because the upper part of the photosphere is cooler than the lower part. An image of the Sun appears brighter in the center than on the edge or limb of the solar disk, in a phenomenon known as limb darkening. The spectrum of sunlight has approximately the spectrum of a black body radiating at about 6,000 K, interspersed with atomic absorption lines from the tenuous layers above the photosphere. The photosphere has a particle density of tilde 1023 meters -3. The photosphere is not fully ionized. The extent of ionization is about 3%, leaving almost all of the hydrogen in atomic form. During early studies of the optical spectrum of the photosphere, some absorption lines were found that did not correspond to any chemical elements then known on Earth. In 1868, Norman Lockyer hypothesized that these absorption lines were caused by a new element that he dubbed helium, after the Greek sun god Helios. 25 years later, helium was isolated on Earth's atmosphere during a total solar eclipse, when the disk of the Sun is covered by that of the Moon. Parts of the Sun's surrounding atmosphere can be seen. It is composed of 4 distinct parts: the chromosphere, the transition region, the corona and the heliosphere. The coolest layer of the Sun is the temperature minimum region extending to about 7 quintillion 5 quadrillion 500 trillion spadesuit 500 kilometers above the photosphere, and has a temperature of about 7 quintillion 3 quadrillion 410 trillion spadesuit 4100 K. This part of the Sun is cool enough to allow the existence of simple molecules such as carbon monoxide and water, which can be detected via their absorption spectra. The chromosphere, transition region, and corona are much hotter than the surface of the Sun. The reason is not well understood, but evidence suggests that alpha-Venn waves may have enough energy to heat the corona. Above the temperature minimum layer is a layer about 7 quintillion 6 quadrillion 200 trillion spadesuit 2000 kilometers thick, dominated by a spectrum of emission and absorption lines. It is called the chromosphere from the Greek root chroma, meaning color, because the chromosphere is visible as a colored flash at the beginning and end of total solar eclipses. The temperature of the chromosphere increases gradually with altitude, ranging up to around 7 quintillion 4 quadrillion 200 trillion spadesuit 20,000 K near the top. In the upper part of the chromosphere, helium becomes partially ionized. Above the chromosphere, in a thin transition region, the temperature rises rapidly from around 20,000 K in the upper chromosphere to coronal temperatures closer to 1 million K. The temperature increase is facilitated by the full ionization of helium in the transition region, which significantly reduces radiative cooling of the plasma. The transition region does not occur at a well-defined altitude. Rather, it forms a kind of nimbus around chromospheric features such as spicules and filaments, and is in constant chaotic motion. The transition region is not easily visible from Earth's surface, but is readily observable from space by instruments sensitive to the extreme ultraviolet portion of the spectrum. The corona is the next layer of the Sun. The low corona, near the surface of the Sun, has a particle density around 1015 meters -3 to 1016 meters -3. The average temperature of the corona and solar wind is about 1 million -2 million K. However, in the hottest regions it is 18 million -20 million K. Although no complete theory yet exists to account for the temperature of the corona, at least some of its heat is known to be from magnetic reconnection. The corona is the extended atmosphere of the Sun, which has a volume much larger than the volume enclosed by the Sun's photosphere. A flow of plasma outward from the Sun into interplanetary space is the solar wind. The heliosphere, the tenuous outermost atmosphere of the Sun, is filled with the solar wind plasma. This outermost layer of the Sun is defined to begin at the distance where the flow of the solar wind becomes super-alpha-venic, that is, where the flow becomes faster than the speed of alpha-Venn waves, at approximately 20 solar radii. Turbulence and dynamic forces in the heliosphere cannot affect the shape of the solar corona within, because the information can only travel at the speed of alpha-Venn waves. The solar wind travels outward continuously through the heliosphere, forming the solar magnetic field into a spiral shape, until it impacts the heliopause more than 50 astronomical units from the Sun. In December 2004, the Voyager 1 probe passed through a shock front that is thought to be part of the heliopause. In late 2012, Voyager 1 recorded a marked increase in cosmic ray collisions and a sharp drop in lower energy particles from the solar wind, which suggested that the probe had passed through the heliopause and entered the interstellar medium. Photons and neutrinos. High-energy gamma-ray photons initially released with fusion reactions in the core are almost immediately absorbed by the solar plasma of the radiative zone, usually after traveling only a few millimeters. Re-emission happens in a random direction and usually at a slightly lower energy. With this sequence of emissions and absorptions, it takes a long time for radiation to reach the Sun's surface. Estimates of the photon travel time range between 10,000 and 170,000 years. In contrast, it takes only 2.3 seconds for the neutrinos, which account for about 2% of the total energy production of the Sun, to reach the surface. Because energy transport in the Sun is a process that involves photons in thermodynamic equilibrium with matter, the time scale of energy transport in the Sun is longer, on the order of 30 million years. This is the time it would take the Sun to return to a stable state, if the rate of energy generation in its core were suddenly changed. Neutrinos are also released by the fusion reactions in the core, but, unlike photons, they rarely interact with matter, so almost all are able to escape the Sun immediately. For many years, measurements of the number of neutrinos produced in the Sun were lower than theories predicted by a factor of 3. This discrepancy was resolved in 2001 through the discovery of the effects of neutrino oscillation. The Sun emits the number of neutrinos predicted by the theory, but neutrino detectors were missing 2/3 of them because the neutrinos had changed flavor by the time they were detected.